Good morning, dear students. Welcome back. I am Dr. Nagaraj, Physics Professor and also Head of the Department of Physics, Bangalore Institute of Technology. So I am teaching physics for engineering students for the past 30 years. I have already uploaded several videos on engineering physics for 2018 scheme and 2021 scheme. So you can check all my previous videos using the link given in the description box. Already several students have got benefited by watching these videos. I am receiving very good comments from them, very good feedback from them. So now many of them are requesting to make videos on 2022 scheme engineering physics syllabus. Well, our VTU, that is Vishwesvaraya Technological University, has introduced stream specific physics. It's a very good idea, excellent idea. Perhaps VTU is the only the university apart from IITs and IIScs where you can see the physics for particular stream specific physics they have introduced. Okay, like civil branch there is engineering physics, mechanical stream there is separate engineering physics, like that. Even computer science and related there is a physics which is totally different from electrical and electronic stream, like that. So totally 4 schemes have been introduced and all of them are well structured, well framed papers. So syllabus is well designed by eminent personalities, eminent faculty members. Well, now in a computer science allied branches like information science, AI, ML, or computer science, or artificial intelligence, or robotics, data science, etc. There is one particular topic called quantum computation. Quantum computation, I tell you dear students, is going to be the future technology. So today with this video I am going to start with quantum computation. I will take you into the world of quantum computation. Before I start with quantum computation, let me tell you something about the role of physics and importance of physics in engineering. See, when Maxwell designed those 4 famous equations, okay, a new branch called communication got opened in technology. Till then there was no question of propagation or transmission of waves. So electromagnetic wave concept was given by Maxwell based on those 4 famous equations. Well, you are going to study those equations in the subsequent semesters. And next, when James Watt, okay, much earlier to that only, when James Watt came out with the steam engine, okay, which was totally based on some fundamental laws of thermodynamics, heat engine came into existence, refrigerator came into existence, and Carnot engine told you what efficiency an engine can achieve, why it is impossible to achieve 100% efficiency. See, you take any branch of engineering, you can see the flavor of physics over there. Okay, well, coming back to first computer which was designed in 1946, it is named as ENIAC. Okay, it is actually short form. It stands for electronic numerical integrator and calculator. See, it was not called as a computer, it was called as a calculator. It was designed in 1946. I tell you some specialities of this computer. Okay, before that I go back to 1900 when I come back to this ENIAC later on, just after 2-3 minutes. I forgot to mention modern physics concept. In 1900 Maxwell gave the concept of quantization of energy. I think your teachers have already taught you about the quantum mechanics, modern physics, okay, and Schrodinger wave equation, particle in one-dimensional box. All those things you might have studied. If not studied, you can check all these things in my YouTube channel. Okay, so all these details are available, so you refer to the following link. So when modern physics was opened in 1900, when Max Planck gave the concept of quantization of energy, okay, it opened a new era in the physics, thereby a new era in the technology. Okay, so later on came what is called concept of atom, structure of atom, and the different spectral lines emitted by different elements. Okay, so like this many things. Einstein explained photoelectric effect, okay, and then Compton effect, and then de Broglie came out with matter wave concept, and that matter wave concept gave birth to, you know, what is called electron microscope. Today using electron microscope you can see atoms. See, it was once upon a time it was believed that it is impossible to see the atoms, but now you can see atoms with the help of electron microscope. Okay, so like that physics is evolving continuously and it is going to assist the growth of technology also. Back to this. In 1946, when first electronic instrument called ENIAC was designed, it was fully made up of vacuum tubes. Dear students, you are this generation students, okay, present generation, 21st century students you are. Actually, initial electronic industry was totally based upon vacuum tubes. Vacuum tubes are very new to you, very, not known to you. Okay, I cannot say it is new to you, they are all very old. And you are not known to vacuum tubes. Vacuum tube is consisting of a bulb type structure, dome-like structure. Inside there will be some filament, some electrode, some plate, something like that. Okay, so these vacuum tubes were occupying a lot of space, but they were able to execute some of the works like amplification, rectification, switching, etc. So initially, in the beginning of 20th century, full of electronic industry was based upon vacuum tubes only. Okay, so the two major disadvantages of the vacuum tubes are it occupies a lot of space. First disadvantage. Second disadvantage, excess heat gets generated during the operation of vacuum tubes. But what to do? There was no alternate. People were inevitably using vacuum tubes for all the electronic instruments designing, be it radio, be it television, be it radar, be it wireless or telephone, whatever it may be. You name any electronic instruments of olden days, they were all made up of vacuum tubes only, and this is not an exception. ENIAC had in fact 18,000 vacuum tubes. Just imagine 18,000 vacuum tubes. And you know how many circuits were there in that ENIAC? There were about 110,000 circuits in that ENIAC. 110,000 circuits made up of 18,000, yes, what? Vacuum tubes. And you know the weight of that computer. Hold your breath. That computer was not just 10 gram or half kg or 1 kg or 2 kg. Today your computers are very simple, very small. Your mobile is a computer. Okay, it is not even half kg. Your laptop is a computer. It is not even 2 kg or 3 kg. Desktop is a computer, but all of them are lightweight. But you know what was the weight of this computer? Yes, it is 30 tons. Weight was 30 tons. And you know where it was kept? It was not kept in the pocket, and it is not possible to keep it in the pocket like your mobile phone. Dear students, just you compare today's computer with this first computer came in 1946. You know, this computer was not placed on the table, not placed on your lap, not in your pocket, not in a room. It was placed in a ground of area 160 square meter. 160 square meter area it occupied, and it was operated by a team of people, not one person or two person. About 10 to 15 persons were operating this system, and not for a continuous period of time, not more than half an hour, maximum of half an hour they could run this system. This was the beginning of first computer in 1946. But now today you cannot imagine this. If I mention all these things, it appears like a story, it appears like a fiction. Yes, that day it was reality. Today it is a history. Okay, tomorrow whatever you mention today is going to be the reality tomorrow. So in science there is famous statement, today's fiction going to be tomorrow's reality, right? Suppose if somebody has mentioned in 1946 that a day will come when you can keep your computer in your pocket, people would have laughed at him. But what is happening? You can keep your mobile in your pocket. Okay, computers, mobile phones, there is hardly any difference, right? Why? How it happened? It's all because of semiconductors. When semiconductors came in 1948, just 1 year after India got independence, okay, it created revolution. In fact, 20th century major breakthrough, scientific breakthrough, if you list, I tell you, semiconductors, lasers and optical fibers will definitely find their place in first 10. Okay, if not 1 or 2 or 3, one of the places in 1 to 10, the semiconductor will find the place, and of course laser and optical fibers also. So when semiconductors came, then first kind of industrial revolution, electronic revolution took place. Okay, so semiconductors replaced our ancestors, distant ancestors. Whom they replaced? Yes, vacuum tubes they replaced. So today we have transistors. You might have done experiment in physics lab, or you might have done experiments in second PUC. You have seen transistor. What transistor you see there is actually a very bigger one. Okay, but compared to vacuum tube, that transistor is small only. In transistor, you know, there is emitter, base, collector. Same jobs, same operations we have even in vacuum tubes also. So vacuum tubes are successfully replaced by transistors. And transistors, when they came in the designing of microprocessors, when they came into the integrated circuits, computers saw a metamorphic change. Okay, so every year there was a revolution, and thereby in 1965 one person by name Moore, G. Moore, is a co-founder of Intel company. You know what is Intel? Intel is the Intel microprocessors. It is a famous company. The co-founder of Moore saw the growth rate of computer development, and he came with a conclusion. He made a statement which we now call as Moore's law. Okay, what statement he made? See, 1946 the first computer was made up of vacuum tubes. From 1946 to 65, almost 20 years, semiconductors removed the vacuum tubes from the scenario. Vacuum tubes were once for all depleted from the region, depleted from the electronic world. Here and there they were in use, but by and large, almost all the not only computers, any instrument, radar, wireless, telephone, radio, anything, television, everywhere transistors started finding their role, and they were doing much better than vacuum tubes. The efficiency was excellent, and size was very small, performance was very good, and the speed, there was no comparison between vacuum tube version computer and semiconductor version computer. So because of the semiconductors, means transistors and other semiconductor devices started playing major role in electronic industry. So the demand for semiconductors, a number of semiconductors to be kept in a particular size of integrated circuit started increasing like anything. After seeing the growth rate, Moore said, underline this sentence, follow this sentence. If the number of computers housed in a particular size of IC, let us say this is 1 centimeter by 1 centimeter, the number of semiconductors to be kept in this integrated circuit, either diode or transistor, I simply call it as semiconductor device. So number of all these dots you can call it as a semiconductor device. For time being and for sake of explanation, I treat them as transistors. So according to Moore, the number of transistors packed in a given size of integrated circuit gets doubled in every 18 months. Every 18 months the number gets doubled. And not only that, cost of the computer reduces to 50%. This is called Moore's law. I repeat, according to Moore, the number of transistors to be housed, to be packed, to be arranged, to be kept in a given size of integrated circuit doubles every 18 months, and the cost of the computer reduces by 50%. And not only that, he said efficiency, performance, speed, everything keeps on increasing. This is what Moore said. And also he predicted one thing. In 1965, the number of transistors in a given chip, there were only 1000 semiconductor devices. That was in 1970. In a given size, maybe 1 centimeter by 1 centimeter or 1 inch by 1 inch. 1 centimeter by 1 centimeter or 1 inch by 1 inch area, the number of transistors arranged was just 1000 when in 1970, almost 50 years back. You know now how many transistors we have in the same area? He predicted, see, this is not a law actually, it's only prediction. After observation he made the prediction, which we now call it as a law. He said by 2020 there will be huge demand for the transistor in a given area. It increases to 10 to the power of 8 by 2020. This is 2020, sorry. This is 2020. Well, by 2020, number of transistors in a given area increases to 10 power 8. This is Moore's law. Okay, so what is Moore's law? State Moore's law. Moore's law says number of transistors to be arranged in a given area of IC increases almost linearly. By 2020 it will reach 10 power 8. Yes, we have reached that. Okay, we have reached that point. And not only that, he said size of the chip decreases, number of transistors increases, size of the chip decreases from centimeter level to nanometer level. Yes, we have reduced the size also. Size reduced from 1 centimeter level to 10 nanometer level. So in 1970 it was 1 centimeter. Today we have about 10 to 100 nanometers chip. Such a small chip we have. Okay, see, one thing you have to observe: size decreases, number increases. Size decreases, number increases. So this is what Moore said. Okay, size decreases, number increases. Okay, now you take one example. This is your college desk size. This is the college desk size. This desk can accommodate 3 students comfortably. Let us say A, B, C students, they can sit comfortably. So here I take students as transistor, desk as a chip, right? Chip size is about 5 feet. Chip size is 5 feet. And each student dimension is 1 feet, let us say 1 feet width. Then these 3 students occupy 3 feet area, 3 feet space. Still you have 2 feet space in between. Got it? So this is A's domain, this is B's domain, this is C's domain. Still you have space here. Right? Okay, sir, there is enough space. Now I bring 2 more students and will ask them to sit here and here. Well, let us say D and E will sit. Now what happens? The spacing between them decreases. Yes, decreases. How many students are occupying? 5 students. 5 students are accommodated. Now you keep on increasing the number of students in the desk. What will happen? Yes, there will be a stage. You reach a stage where there will be no more further addition of students. If the disk can accommodate 5 students, at most by pressing them, by pushing them, because our body is little bit flexible, so we come adjust ourselves and accommodate 1 more person, 6th person, 1 more person we will accommodate, 6th and 7th person. Beyond 7 I cannot accommodate. Okay, so that means if you cannot accommodate any more transistors, any more students in the given chip, any more transistors in the given chip, this is chip means desk, chip means chip only here. So if you cannot accommodate any more transistors there, that means Moore's law ends there. Moore what said? Moore said number gets doubled. Today I have 10 power 8. Today I have 10 power 8. Next 2 years, actually next 18 months, okay, I will take it as 2 years only. After 24 months, 2020, okay, today it is 2023, let us say. After 2 years, that is 2025, if I go, I must put double of this, means 2 into 10 power 8, 2 into 10 power 8. If I cannot accommodate 2 into 10 power 8, that means that is the end of the Moore's law. Now the $1 million question. Sir, have we reached that stage? Yes, we have already reached that stage. We have reached a stage where you cannot increase the number of components, number of transistors in the IC. We have reached that stage. Sir, what happens if I keep on putting the semiconductor devices continuously? What will happen? Yes, this is a beautiful question. Sir, if I increase the number of components, okay, like if I increase the student, what will happen? If I increase the number of components, what will happen? Yes, what will happen? I tell you. Okay, this is one desk. Okay, now I take the same example, I put it in some other form. Just listen here. This is one desk, this is one desk, this is another desk. Okay, this is a desk 2, this is a desk 1. Okay, one student is sitting here, let us say A is sitting here, B is sitting here. As long as the desks are separated by this much gap, definitely and B are distinct. They have their own path. They have their own identity. A never interferes with B, B never interferes with A. Just you recall your classroom. In classroom, how you are sitting? You have one row of desk, after that a small gap, walking space, again there will be desk. Again there will be space, again there will be desk, like that, okay? So you consider 3 desks or 2 desks in a row like this, one after the other, one after the other, desks are arranged, okay? Now, suppose if the student A moves little bit, he will not fall off the desk. Little bit he will push. In Kannada we call it as jargodu. So if he push little bit, if he moves little bit, ಸ್ವಲ್ಪ ಜರುಗದ ಅನ್ಕೊಳ್ಳಿ, he will not come out of the desk, right? Suppose he moves little bit, definitely he will come out of the desk, he will fall into this gap. Same thing from B also. If B moves little bit this side, definitely he will come out of the desk. That is very expected happening. Now do one thing, move the desks little bit towards each other. Keep on moving. That means you reduce the gap, you reduce the size. What will happen? Definitely, at one stage, there will be very small gap. That gap is less than the size of this boy. Okay, if the gap is less than the size of the boy, guess ಮಾಡಿ ಏನಾಗುತ್ತೆ? If the 2 desks are very close but not in touch, they are not in touch, very close, A moves little bit, ಸ್ವಲ್ಪ ಜರುಕೋತಾನೆ ಅಂದ್ಕೊಳ್ಳಿ, whether he come out of the desk, yes he will come out. Whether he falls into the pit, no, desk ಇಂದ ಹೊರಗಡೆ ಬರ್ತಾನೆ, ಕೆಳಗಡೆ ಬೀಳೋದಿಲ್ಲ. Where he will go? He will shift into the next desk. That means he will go from A to B. He will go from A to B. I hope you got this example. So when the gap between the desk reduces, then the student will move into the next desk, he will tunnel into the next desk. Almost same thing will happen here. Here what actually happens in transistors, electrons are flowing or holes are flowing. Okay, let me take any one, let us say electrons. When electrons flow, they constitute current. As long as transistors are individual, electrons will flow in their own transistors, from emitter to base, base to collector, collector to emitter. They will have their own circuit. Transistor 1 will never look at transistor 2. Desk 1 will never look at desk 2. Okay, suppose if the transistors come very close, if the gap reduces less than a nanometer, you know what is nanometer? 10 power minus 9. The 10 power minus 9 is a distance not between the transistors, man. It is a distance between the atoms. Atoms separation. The gap reduces such a small value. ಅಷ್ಟು ಕಡಿಮೆ ಆಗಿಬಿಡುತ್ತೆ. ಅವು ಎರಡುಗಳ ಮಧ್ಯೆ ಇರೋ ಗ್ಯಾಪು atomic size ಇನ್ನಷ್ಟು ಬಂದುಬಿಡುತ್ತೆ. When the gap reduces to atomic size, what happens? Yes, your guess is correct. Exactly this will happen. If A moves towards B, he will enter into the desk 2. Like that, if this is transistor 1, this is transistor 2, if they move very close to each other, if the gap reduces less than a nanometer, then electron from here will tunnel into this one. This is called tunneling effect. So transistor 1, T1 electron will totally get into T2. If that happens, the happenings will be totally unpredictable and the result will be totally different. What actually you expected the transistor to do will not happen. Transistor functioning will change. You are designing a circuit with the help of transistor. You have designed logic gates using transistor. If the transistor itself is not working properly, then your gates will become waste. Your gates become waste, circuit become waste, overall function of the computer will come to a halt. See, transistors, gates, processors, and then a language, and then a performance. Like that, a hierarchy of the computer is. Basically it is transistor or semiconductor. If something happens at the transistor level itself, definitely the overall function will be hampered. Like if I am correct, transistor is something like our blood cell, it is something like our blood. If something happens to the blood, definitely it will reflect in the body in form of some other diseases. So like that, if something happens to the transistor, within the transistor, if electrons are totally misfocused, obeying. If totally behaving in a different manner, then definitely transistor will not function. Okay, this is what is going to happen if the spacing keeps on reducing. Sir, do you mean to say that in near future our present computers are going to become waste? No, I am not telling like that. I cannot say, I should not say today's computers are equally efficient and they are going to be there even in future also. But we are reaching what is called threshold. We are reaching that barrier beyond which we cannot increase the performance speed, we cannot increase the storage capacity, we cannot go for any evaluation. Actually, when first computers came in 1946, it was a very low memory storing device. In fact, there was no output option at all. Slowly memory capacity increased, efficiency increased, performance speed increased. See, the computer performance speed we measure in terms of what is called flops, floating operation point per second. Earlier it was about 10 power 3 means 1000 flops, 1000 floating point per second. Today we have more than 10 power 13 flops. Just imagine, where is 10 power 3, where is 10 power 13? So performance speed we have increased, and demand is like that. Okay, so usage of computer is becoming order of the day, and the computer is entering to various domains nowadays. Okay, so performance speed is increasing, and even in future also we have to increase, but what to do? There is a limitation now. According to Moore, you cannot put many more transistors into a given small area. If you put, what will happen? Yes, this is quantum tunneling and other peculiar effects will come into picture. So then what to do? Is it end of the growth? No, physics is always there to give you solution. There is a ray of hope. Physics gives you a ray of hope in terms of what is called quantum computation. So quantum computation is the best solution for this problem. Quantum computation is going to give you a satisfactory answer, and it is going to solve all the problems. In fact, I tell you, many countries including India already saw the importance of quantum computation, and they are doing a lot of research. You students must be lucky to study this quantum computation in the first semester itself, because this is a very hot favorite field for master studies, MS studies. If you do quantum in quantum computation, definitely your destiny will be in a very higher level. I tell you, IBM company has invested billions of dollars. China has invested 10 billions of dollars on the quantum computation research. India, we are not lagging behind. Our government has invested 8,000 crore rupees on quantum computation. Our Honorable Prime Minister mentioned the importance of quantum computation in recent Science Congress function. Very recently in January, it was 2023, it was held, and the Prime Minister mentioned the importance of quantum computation. So we are going to have a solution for this problem in terms of quantum computation. So I am going to explain the fundamentals of quantum computation in my lecturing. Please stay with me. I will try my level best to make the things as simple as possible. I may use small Kannada words here and there. Okay, those who are watching this, those who don't know Kannada, they also can understand. Don't think that sir, whatever is explained in Kannada is not explaining in English. I explain in English, but for the benefit of our students, Karnataka students, I am explaining little bit, very little, even in Kannada also. I hope you are comfortable with my presentation. Okay, thank you very much.